Hello, thank you so much for tuning into my YouTube channel. Today's video is going to be a tutorial on principal component analysis and non-negative matrix factorization in Python. I'm going to also draw a quick comparison between them. Let's get started. As I said, this video is going to be an introduction to PCA and NNMF in Python. PCA stands for Principal Component Analysis and NNMF stands for Non-Negative Matrix Factorization. PCA is a widely used technique in statistics and machine learning for dimensionality reduction. It helps in reducing the number of variables in a dataset while retaining as much information as possible. By transforming the data into a set of orthogonal or uncorrelated principal components, PCA helps in capturing the most significant variance in the data. PCA is used in data visualization, noise reduction, feature extraction, and image compression. In the case of the data visualization, high-dimensional data can be challenging to visualize. PCA reduces the data to 2D or 3D, making it easier to plot and understand. In the case of the noise reduction, PCA can filter out noise by reducing the dimensionality of the data and focusing on the most significant components. For feature extraction, PCA is used in creating features for machine learning models by capturing the essential patterns in the data. And the image compression can be done by keeping only the most important principal components. Non-negative matrix factorization, or NNMF, is a matrix factorization technique that breaks down a non-negative matrix into two smaller non-negative matrices. This makes it particularly suitable for data where non-negativity is important, such as pixel intensities in images, word frequencies in text, or gene expression levels in bioinformatics. NNMF can be used in image processing, text mining, and bioinformatics. In image processing, NNMF is used to decompose images into parts-based representations such as facial features or components of an image. In text mining, NNMF can be used to discover topics by decomposing document term matrices. In bioinformatics, NNMF is used to uncover patterns in gene expression data, revealing underlying biological processes. Both PCA and NNMF has dimensionality reduction and basis function extraction in common. In other words, both PCA and NNMF reduce the number of dimensions in a dataset, simplifying the data while retaining essential information. And in the case of the basis function extraction, both techniques extract basis functions or components that represent the original data in a compressed form. But they also have some differences. The first one is orthogonality versus non-negativity. PCA components are orthogonal, or in other words, they are uncorrelated, which means they provide a purely statistical basis for data reduction. NNMF components, on the other hand, are non-negative, making them more interpretable, especially when parts-based representation is needed. The second difference that they have is their interpretability. NNMF tends to produce more interpretable results, especially in cases like image or text data, where the components often correspond to meaningful features, such as facial features in images. And the third difference that they have is linear versus nonlinear relationships. PCA is linear and captures variance in the data based on a global linear transformation. NNMF, while still linear, is better suited for capturing localized parts-based structures in data. Let's go to Python and see an example of both PCA and NNMF there. Here, PCA and NNMF are applied to the digits dataset, which is a common dataset for handwritten digit recognition. Digit dataset, which is from scikit-learn library, contains 8x8 grayscale images of handwritten digits. There are 1,797 samples in total with 10 classes, digits from 0 to 9. The pixel values range from 0 to 16, representing the intensity of each pixel. And this dataset is not the same as MNIST dataset. Okay, here are the libraries that we're going to use, as you can see. And this is where we're going to be loading the digits dataset. And here we report the reconstruction error, which gives us an idea of how much information we lost by reducing the dimensions. So we first reduce the dimension and then we reconstruct it and we report the error. And we do it for both PCA and NNMF. So we first compress the data and then we reconstruct the data and then we report the error. And as I said, this would give us an idea of how much information we lost by reducing the dimensions. And this is where we're going to be plotting the error of reconstruction. And then I'm going to show you the cumulative variance plot, which shows how much of the total variance in the data is captured as we increase the number of components. This is easy for PCA, but in the case of the NNMF is not as straightforward. So I had to approximate the cumulative variance for NNMF. Since NNMF doesn't have a concept of variance explained like PCA, I used a simple approximation by calculating the reconstruction error as a fraction of the total variance. This gives us an idea of how well NNMF captures the data as we increase the number of components. As you can see, this is being done here. So in other words, to approximate the variance explained for NNMF, we use this method. We have the reconstruction error already calculated, and we compute the total variance of the data, and then we put it in this formula to approximate the variance explained for NNMF. As I said, this approximation gives us an idea of how well the NNMF components are capturing the overall structure of the data. Let's run the code and see what happens. Okay, the run is complete, and as you can see, this is the reconstruction error for both methods. As you can see, the reconstruction error goes down as the number of components increases, which makes sense. And it's the same for both methods. And this is the cumulative variance explained for PCA. And as you can see, the variance increase as you increase the number of components, which makes sense. And the same is true of NNMF. In other words, the approximate variance increases as you increase the number of components. So these two plots for PCA and NNMF give us an idea of how well these methods were able to capture the data as we increase the number of components, as I explained before. And that's about it. Thank you so much for watching this video. I hope you liked it and you were able to get something out of it. If you liked it, I would appreciate it if you could subscribe to my channel and also share the video with your friends. Thank you so much and have a nice day.